What causes 1 in 9 deaths worldwide, affects 80% of people living in cities, but is often invisible? What leads to more than a quarter of deaths from heart disease, 34% of deaths from stroke, kills almost as many people each year as the number of breaths you take? The answer: air pollution. First step in reducing air pollution is efficient and reliable monitoring, and our project aims to do just that. You could access the real-time air pollution values of any location, anytime, anywhere in your fingertips. Let's get into the presentation and see how this works. IoT-based real-time air pollution monitoring system. How are we different? The existing solutions provide air pollution status only at a specific fixed station or a location. These monitors are read all day and the values obtained are redundant and a lot of power is wasted. Our solution reduces the redundancy of the monitor by mapping a wide area instead of a fixed location. It also improves the reliability of the status by localizing the data. And we have the map or results at our fingertips, and also the user can subscribe for regular updates. Here's how it works. Our project consists of 3 main units: the data collection unit, the data processing unit, and the display unit. The collection unit is fixed in a vehicle or a truck. So when this vehicle or a truck is operated, this data collection unit is periodically and regularly turned on to record the pollutant values at that location. So the pollutant values along with the geolocation and the timestamp is pushed to a Google Sheet through Wi-Fi. We are calculating the AQI values from the obtained data, and the calculated AQI values are projected onto a map so the user end can access the map.
To the hardware part, the components used are Arduino Uno MQ9 sensor module used to detect CH4CO and LPG, MQ135 used for detecting ammonia, PM2.5 dust sensor, GPS module, Node MCU, multiplexer, breadboard, jumper wires, capacitor, resistor. Before using the sensors for interfacing, it should be calibrated so that they yield accurate measurements. Two methods used for interfacing are software serial communication and multiplexing. Software serial communication method, we use Node MCU and Arduino microcontrollers here. Arduino reads the data and the data gets printed in the serial monitor. The RX and the TX pins in the Arduino are connected to Node MCU's digital pins, where it reads the data in the serial monitor. Using the read string until function, the data is recovered. The MQ9 and MQ135 sensors are interfaced in Arduino in the following way. The dust sensor is interfaced in this manner. GPS module is interfaced. Node MCU is interfaced with Arduino. Second method is multiplexing. Since the Node MCU has only one analog pin, and this multiplexer here is used to retrieve the state of several analog sensors. This is how the sensors and the Node MCU are interfaced with the multiplexer.
Here comes the description of our data storing unit. Google Sheets. The collected data in the Node MCU is transferred to Google Sheets where it is stored. The G Sheet acts as a base where information from all the units gets stored, which can further be used for processing purposes. The deployment key is used for interfacing the hardware and the G Sheet. Google App Scripting is used to achieve this. AppScript is a cloud-based development platform for creating web applications. It helps in integrating various Google products. It is based on the JavaScript language, where we alter the script of the G Sheet to make it auto-updating once it gets a URL request. The web application can be shared by deploying it. Data can be pushed into Google spreadsheets in 2 mechanisms, push and pull. Here in our project, we have employed the push mechanism. In the push mechanism, the hardware sends a request with data to a Google server, running a script that will in turn add the data to the spreadsheet. 2 setups are to be done for the data processing unit. Node MCU setup. A HTTP library has to be used to send a request. Here, Wi-Fi client secure class is used. It implements support for secure connections using TLS transport layer security, which is an encryption-based communication protocol. A function called send data is used to push the data into G Sheets. This function generates an URL with the data information and deployment key of the Google Sheet. So setup required in G Sheet The sheet and its script are given a name. The columns in the sheet are also labeled appropriately. The script is programmed such that it receives the request sent by hardware and adds the data to the corresponding columns. It is interfaced with the sheet by the help of the sheet's ID. Later, it is deployed as a web app. This allows the sheet to get updated with just an URL. The connection is closed after sending each set of values. And we can see that this cycle continues as long as the hardware is active.
Processing the data. The Google Colab acts as the processing unit of our system. It transfers the collected data from the Google Sheets and processes it to find the AQI at a particular region. The AQI calculation followed in our system is based on the guidelines provided by the CPCB. The CPCB classifies 8 pollutants as major parameters for deriving AQI. As monitoring 8 parameters can prove to be difficult at certain regions, a minimum of 3 pollutants have to be monitored to find the AQI at that particular region. And the subindices of these pollutants should be based on at least 16 hours of data. The pollutants considered in our system are CO, NH3, and PM2.5. According to CPCB's air quality standards, AQI is categorized into 6 severity levels. Data handling in Google Colab. To access the documents in the Google Drive, the Colab takes the help of PyDrive, a high-level Python wrapper which allows the user to easily upload, download, and delete files in one's Google Drive from a Python script. Before accessing the documents in the drive, the account has to be authorized or verified. To transfer the data from Google Sheets to Google Colab, GSpread library is used. The required Google Sheet can be accessed by its URL, name, or deployment key. For efficient handling of data, it is converted into data frame objects using Pandas library. Output of our project. After calculating the AQI and the severity levels, the output data is visually represented in the form of color-coded maps. Here, the AQI value are projected on an OpenStreetMap and are color-coded based on its severity levels. This is the map generated at the Colab, and these are the calculated AQI values by the units deployed at these regions. Some of the additional features that are developed as part of our project are a web page and a system that sends mail. The output, that is the color-coded map, is generated at Google Colab and hence it is not accessible by everyone. In order to combat that, a public URL is generated. This is the web page. Whereas the mail system can send alert mails to the user whenever the air condition around them becomes poor.
Now let's see the application of our project. This setup can be deployed in many of the countries to monitor the dangerous gas level that is harmful to the people, so that the authorities would take an immediate measure to control the cause. The next is the individual can check the air quality at both the indoor and outdoor level, so that they'll be more cautious and informative about their particular location. This will also be used efficiently when it gets equipped in a moving garbage trucks. If you see, each area has its own garbage truck, so that when it roams over the area, the air pollution gets measured locally at that particular place. It also plays a vital role when it has been installed in such factories and mining areas, which measures the amount of hazardous gas being released. The conclusion of a project. There will be an instant updation of values with the visual output, so it makes it to be a user-friendly one. And this also get accused to open map. If you see in cases like when it pinpoints the reddish color, then the individual or the user can come to the conclusion that something dangerous is happening at that particular location. So this makes the user more informative about that specific location with respect to the atmosphere gas levels. And moreover, to say that our project is a compact one with a real-time system, so that it can be fitted at any places, and it also works the more efficient way. The future scope of a project. We have to increase the number of gas sensors so that it measures the various gases present in the atmosphere, and it will be also used for furthermore applications. And the values of the AQI must have to be highly precise. And we have also planned to create an app using MySQL and HTML languages. And we have to also look for an alternative database instead of what we have used like the G-Sheet and the Google Colab. The failure cases, if suppose a fuel is being burned at a heavy rate, then in that particular area, then these gas sensors will measure that a high amount of fuel that has been burnt. So this gives this gives a incorrect value. Then our module is purely dependent on Wi-Fi only. So in absence of Wi-Fi connection, it stops working. And we have used a G-Sheet and a Google Colab, but this fails to get a huge amount of data collection. And the last is, it mainly depends on the sensor quality, as it is directly proportional to the output of AQI value. So when the sensor is not as good as, then we won't get a proper AQI values. So these are the failure cases.
We would like to thank our team mentor Aditya Anna for guiding and helping us throughout the completion of our project. We also express our gratitude to the Robotics Club for giving us this opportunity. Thank you.